Okay, I was saying that we have seen the seismic loads with Professor Gentile, and now we will see how to model it with a software and how to see the results. Then we will move to the reinforced concrete material. You have seen, I think in November, the steel material for the steel structures. You've seen how it behaves under different internal actions, so under compression, under tension, how it behaves when there is combined compression and bending. And you have also seen that it is a material that is very prone to buckling, okay? Because it is a very stiff material, so we tend to have small element, structural elements. I'm trying to see, okay, for example, we have some columns here. And we can see that with respect to concrete elements, the beams and the columns are very thin. So when we have a very thin, very slender elements, there is, we should pay attention to buckling effects. In this case, we move to the reinforced concrete, which is not really a material, but it is the combination of two different materials, the concrete and the reinforcement bars, so the steel bars. Just a little bit of definitions for the mechanical properties, a little bit of background from its very beginning to nowadays, and the material properties. Then we will move to analyze the behavior of reinforced concrete elements under pure compression, under bending, and under combined compression and bending. Obviously, these last, maybe the last two topics will not be seen today, but next week. But it's really nothing so different. You have only to focus on a few important hypotheses that we assume when we study these material properties, and then it will be done. The only topic that remains is the behavior under shear, so il taglio in Italian. Possibly this very last topic will be seen or in the last part of the next lecture or in January. So that there should be time for the first lecture of January, if we desire to hold it, for just a little review of all the course topics and maybe some questions about some doubts from you in view of the exam. Morning. So let's just see, this is a schematic of a masonry tower. Why we want to see, why are we proposing you the masonry tower? Well, basically, this holds both for towers and both for high-rise buildings, so skyscrapers and so on. We have that real structures can be modeled as just cantilevers. Okay, they are vertical elements where we have the vertical dimension that is dominant with respect to the transversal one, and I think most important is that also for the high-rise buildings like skyscrapers or high-rise palaces, we have that we have some levels where the load is concentrated. So typically the floors, the stories, and so on. Well, this is a very important case study for Italy, and not only, because as you may know, we are very rich in cultural heritage buildings, which are actually very prone to seismic damages. Like we have several civic towers or bell towers. So far we are seeing the just the vertical the building, we can assume that each load, each level is has an interstory height of 4 meters. Obviously, there will be the lower sections, the lower cross sections, which are bigger than the upper ones. So it's not really easy to understand. You can see from here, there is, for example, in these two dimensions, the section this is the upper level, so the three upper levels. We have a section that is thinner, more thin than the section at the base. Because at the base we will have a higher compression load, obviously, so the section and the load-bearing walls will be will have higher load and higher sections. But I will go on just showing on here. For the second part, we will use the blackboard. So, okay. So, I want to do this. Okay. Here we have the dimensions in height and in cross section. The H in this direction and B for the other direction. Obviously, we can see that it is a hollow square, both sections. Here we have that the internal square is bigger than, it's very slow, but it is bigger than the lower one, because we have the length of this dimension that is 5.6 meters rather than 5 meters. So we have that the load-bearing walls are more thick of 0.3 meters, so 30 centimeters per each wall. Okay, what do we want to know about this structure for computing any structural analysis? For example, or by hand computation or with TeraUTD or any other software. We want to know the mechanical properties of the material, obviously, and the geometrical properties of the cross-section. So that's why we need the drawing of the sections. And we have seen that the main geometrical properties that we are interested in when we care about bending and is the inertia moment. So I hope that it is obvious for all of you how to compute the inertia moment for a hollow square section. In case it is not, here we have the formula that is very simple. It is just the inertia moment of the bigger square less the inertia moment of the internal one. Okay, so we have 1 over 12 capital B2 times the height to the power of 3 less the dimension of the internal one. We can collect the 1 over 12 out of the brackets. And the same formula holds for the lower section. So we will end up, that we substitute these numbers, these values, and we end up with some numbers that we can, for example, put into TeraUTD. So here I just do the entire computation, and we can see that this is the original drawing of the tower, just rectangular. Because typically, when the section becomes more thin, we are just removing material from the internal side of the structure. This is typically what is done, not always, obviously. So just to how to represent the structure mechanically, we can see that we have a vertical development of the element as if it was just a beam, and the lower part has a stronger inertia as if it is a beam with higher dimensions than the top part. And here we have the dimension of the inertial moment at the top and the inertial moment at the bottom. Okay, now let's just pause it and let's do it with the software. Whenever you want. Okay. Now it will start 1,000 times. Okay. I hope that nowadays it is clear for all of you how to use this software. We can just you can see, people at home can see what I am sharing now. No, you cannot. Okay. That's better. So we have how many levels was it? So we have 6 levels of the structure, so we need 7 points. And okay, that's trivial. It will take us really nothing. The first point is in 0, 0, then 0, 4, 0, 8, 0, 12, 16, and so on. Okay, I think it's right. We have our seven points. We create the elements which connect all the points that we have created. It is important to connect all the nodes because otherwise there will be no possibility to apply the seismic loads. And as soon as I get there, I will ask you how should I proceed. So the main assumption is to have a Clapeyron section at the base of the structure. Obviously, this is true with some limitation, but it's just an assumption, and it means that the foundation of the building and whatever is at the base of the building provides full restraint to the structure and prevents any motion of the structure. So no other restraint. So what about the distributed load? You should have seen with Professor Gentile how the seismic loads should be modeled. Anyone of you remembers? Okay, be honest. Okay, first of all, is it a vertical or a horizontal load? Horizontal. Because what is the effect of an earthquake? It's just a motion, okay? It is an horizontal motion. And we have to remember if we should apply that load at the base or on top, or somehow we distribute it along the structure. So if we apply the load at the base, right here, what do you think it will happen? I mean, we can apply here 1 kilonewton, 1000 kilonewton, all the load we want, and the structure will be undeformed because all the load that is applied here is immediately balanced by the basement. So the restraint here will directly absorb all the load that we provide the structure. So obviously, even if the load, the earthquake comes from the ground, we do not have to apply the load at the base, because what happens is different. We have an imposed displacement at the base, and it's different. So typically what we do is we apply the load along the vertical the vertical I don't remember the words. Okay, along the vertical dimension of the structure. And with Professor Gentile, you have seen that if we put some accelerometer at different levels of the structure, what we record in case of a seismic event is that we record some acceleration which increase more or less linearly with increasing height. Okay, so on the top, and that's what we can experience every time we end up in an earthquake. That if we are living at the first or the second floor, we barely understand that something is happening. If we are on top, we will feel something much stronger. Okay, and for the second dynamic, for the second law of dynamics, the force is mass times acceleration. So basically, if we have an acceleration that is linearly increasing with the height of the level, we can imagine that we can apply the equation is to impose a linearly force increasing, a force that is linearly increasing with the height. So the model was this. We have a triangular distribution of loads applied only at the levels where we concentrate, we lump the mass of the system, and we imagine that all the mass that we have in this part of the section of the structure is concentrated in this point. So the force that is mass times acceleration of this area of the section is concentrated at the level of the story. Yeah.
What about the first half of the first section?
No, we just neglect it because we assume that this part is carried out by the vehicle. Okay, this is just some brutal assumption. Okay, and how do we compute the forces that have to be applied at each story of the... maybe you cannot really read the numbers very well, but you will have all the slides, so don't worry about it. The force is just the global force that is applied horizontally to the structure, so H for horizontal, is just, let's say, related to the weight of the structure, and it is multiplied times a coefficient that varies according to the intensity of the seismic event we want to model. Okay? And then what we do is just we use the formula that I have not reported because I didn't think it was necessary, but it could have been useful, that tell us how to recover the force at each level of the structure, saying that it will be a linear combination of the global force and the height at which we are applying it. So we have that the force at the first level is 640 kilonewton, and at the second level, so it means at the double of the height, here we are at 4 meters from the ground, here at 8 meters. The force at the second level is the double of the force at the first level, and so on, it linearly increases. But the formula is reported in the slides, I think the last slides, where Gentile was explaining you this. So as you can see, there is just the static equivalent forces of the seismic event, and it's pretty simple to model it. So the attribute node force moment at the first level was 640. Wrong. Here I can see that I have, maybe you cannot see it. Okay. I imposed this force as Fy, and obviously the arrow is upward in the vertical direction. That's because I made a mistake. It is Fx. Okay? And so we have the arrow in the right direction. Then 1280 in the second level. At the second level. I don't remember the others. 1920. That is low. Okay. 24, 25, 60. $3,200 and 3840. Okay, here we go. Now we have applied all the seismic loads as previously computed. Now, we have to define the material properties and the geometrical properties of the structure. So, are we neglecting anything? No. So we go on property. Okay. We can look for the material that is measured. Okay, here we have it. Actually, I don't remember if we really have it or if I defined it and saved it. You can check. If you will find it at the bottom of the page, otherwise you will need to add the new material, and we just define 3,500 megapascal of the modulus, you define the law, the name, Poisson ratio is still 0.2, density is 2,000, and thermal expansion, the value holds. So we have the memory, and then the section. Okay, I did a mistake. Anyone can guess the mistake I did? That's very, now it appears very quickly. Remember that we want to define two different sections. Okay, so in order to discriminate the behavior at the base that is stiffer than the upper part of the section of the structure. So, in order to model it with TD, I should have defined two different section properties. Okay? So we will need two. Can I cancel silence? Sure not. Okay, so we have to select these three elements and change the property. Okay, we need to recreate this file from scratch. Sorry. So this grid for the base, and the next grid for the top part of the structure. We have a full restraint at the base. And then finally the loads. Okay. And now we can associate the masonry material to both the property types and finally define the geometrical properties. In this case, we are not dealing with steel structures, and in the past we have always basically used steel cross sections, so that in order to define the geometry, we used to go on geometry and select profili, okay, in order to define the cross section. In this case, it is different because we need to define the geometrical properties. The only geometrical properties that are of interest for us is the cross-section area and the inertial moment. Well, the inertial moment were the ones that were computed previously. Here we have them. And are for the base 1.48 times 10 to the power of 10, obviously in centimeters. Whereas the cross-section area, we will discuss it later. We define the inertia at the top, 1180. Okay. We have two options for the area. Or we compute the actual value of the area and we put this number here. But what will happen is that there is the possibility that the structure will deform a lot in the longitudinal direction. So in case this happens, we have the possibility to increase arbitrarily the value of the section area. And what happens is that basically the area is the geometrical property that opposes to compression and tension. Okay, we have seen it with the stresses, where we said that the normal stress induced by the normal force, so the axial force, has to be compared with the area. Okay? Whereas this is the stress induced by compression or tension. Whereas when we deal with the bending, the geometrical property that opposes to the bending is the inertial moment. So if we want to say that the element is axially stiff, we have to increase the value of the area. So in this case, we can assume, for example, this value for both the elements. This is not mandatory. This is just how to model, for example, something very axially stiff. Okay, so finally we have basically everything and we can run our analysis. Maybe. I am waiting for the software to run. Something is happening. Okay. Okay, this is the result. This is what we obtain. So under the static force that models our seismic event, we have the deformation of the structure that is represented by the purple line. And if I want to magnify it, we can just see that the behavior is obviously the one of a cantilever that is clamped in at the base. So at the base we have no displacement and no rotation, so the beam starts vertical. And then we have that the deformation of the upper level is higher than the deformation of the base. That's obvious, and this is magnified also by the fact that the upper level has a smaller inertial moment of the base sections. And we can see also that, no, that's not important, never mind. This is instead the, okay, you cannot see anything because that's pretty bad, but no, okay, that's bad. As before, we have the diagram of the bending moment, which is linear for each bracket, for each section, for each sector of the structure, and it linearly increases until it reaches its maximum value, and the maximum value of the bending moment is always at the base of the section of the structure. So in this case, it's 222,960 kilonewton times meters. And at the top, the bending moment is obviously 0 because we have no restraint. We have the free end. So when we design the structure, we have to care especially about the first level or the first two levels of the section of the structure. That are the levels where we have the higher internal actions, both in terms of shear force, both in terms of bending moment. And these are the levels where we can see the greatest damages. Axial force, nothing, because we have no vertical force, no longitudinal force. And this is the level of the shear force. Okay, people in class cannot see anything. I hope that people at home can see it better. But basically, we have that the shear force is constant piecewise, and it reaches its maximum at the base of the structure, as I said before. And if we want to investigate the maximum displacement, we can see, okay, using the peak command and investigating node 7, which is the node on top of the structure, the displacements are 0.076 meters, so it is 7.6 centimeters. And this is the maximum displacement we will see in the structure. Now let's back to the presentation. And just resume it. This is how to compute, how to use the structure. This is the deformation. How to investigate the shear force, which is maximum at the base, and the bending moment. Okay, any question about this example? Okay. Now just a very quick another example on something that we have seen something similar, but not really in this context. It is a frame. It's a very simple frame. We have just 3 spans whose length is 5 meters, and the height of the columns is 4 meters. We want to assume a rigid slab. I will not go for TLL2D in order to redo this example because it's very trivial, and I just want to focus on the on the meaning of what we are seeing. Here we have the material, C2530. We will see what this number means in the second part of this lecture. And in this case, the slab represented by the beam is rigid, and all the columns are equal. So okay, we don't need to go with to use TLGD in order to find, in order to understand how to model geometrically this structure. The only important thing is when we define the columns. Here I have used columns of square cross sections, 40 centimeters times 40 centimeters. That is a common dimension for columns in residential buildings. So it means 40 times 40, a cross-section area of 1,600 centimeters square, and an inertial moment of 213,000 centimeters to the power of 4. This is true for the columns, but for the beam that connects the top of the columns, I am, as I showed you before, assuming arbitrarily high values of cross-section area and inertial moment. That's why I want to stress that the beam is extremely rigid with respect to the columns. So the behavior of columns which deform together with the beams, we'll see that all the deformation will be on the side of the columns. That's what happens usually for the buildings. Where we have slabs in concrete, we cannot see it because we have the covering of the slab, but the slabs are usually extremely rigid in their plane. Okay, now if we assume just an horizontal force imposed at the top of the structure, that can be assumed as a seismic load in the case of a building that has just one story. That means one force applied at the story level. In this case, 1,000 kilonewton is just something to show you. It doesn't mean anything. But if we look at the distribution of the shear forces, we can see that all the columns are undergoing shear forces of 250 kilonewtons. This means that if we have a system with different elements that are equal both in terms of restraint and both in terms of cross-section, we have that the internal actions will be equal for all the structures. This is true for the columns, and this is true for the shear force, and this is true also for bending moment. And just something that I want to stress from here, something that maybe we didn't pay so much attention during the course because we had no time, but if we look at, okay, first of all, people in the room cannot see the numbers. On top we have 499 kilonewton meters and 500 kilonewton meters at the base of the columns. So basically the columns are clamped in at the base and also clamped in almost at the top because they are connected to a beam that is rigid. So we guess that the beam will deform in this direction, will just translate, and all the columns will have the deformation typical of a clamped in beam. And it is important to notice that the bending moment in this node of the beam is exactly the same of the bending moment at its base, at the base of this node on the column. Whereas when we have an internal node, we will have that this is node 7. If we just magnify this node, we have that. We have a bending moments equal to 394. I will do kilonewton times meters. I will not write it every time. On this side, we have 105. Kilonewton times meters. And at the base of the column, 500. Okay, I have just neglected the decimal numbers. But what is important is that when we focus on any part of the structure, even the internal nodes, there is an equilibrium that is satisfied. In this case, the node is undergoing 500 kilonewton meters in clockwise direction, and 105 plus 394 dot blah, blah, blah. That means 500 kilonewton meters in the counterclock direction. So basically, we have that the sum of the moments applied on the internal node is equal to 0. That's the equilibrium with respect to the rotation of this node. Okay, we have already seen this stuff. Okay, now what happens if we run the analysis again? But in this case, the second column is 5 times stiffer than the others. What happens is basically that the deformation of the structure will be basically the same. Okay, we have just the top of the structure that is translating in that direction, and since the beam is actually rigid, actually stiff, we have that the deformation on top of all the structure, of all the columns, will be the same. But when we have a system where we have one element that is way stiffer than the others, it means that that element will undergo higher forces. This is true for the mechanics, this is true for all the things that we can meet in the life. When two people are undergoing a tough period, it will be always the stiffer one that will have to carry the greatest part of the load. This is true for everything, also for mechanics. And if we compare, no, you cannot read the numbers. This is the plot of bending moments diagrams in the structure, assuming that the second beam is more stiff than the others. We can see that the bending moment of all the beams, of all the columns, here, here, and here, at the base is 249 kilonewton meters, whereas here we have 1,253 kilonewton meters. That is way bigger than 500 that we had before. Okay? So we are stiffening one element, and that element will undergo higher internal forces. Okay, this is just didactic, something to show. We just created elements, columns, which are proportionally increasing with the order of the column, whose stiffness is increasing with the order of the count. So this is twice stiff as this is 3 times, and this is 4 times. And when we check the results, we have that internal forces, here is the bending moment, 200 at the base, 200 kilonewton meters, 400, 600, and 800. So when we have a system in series with not homogeneous stiffness over the elements, we will also have not homogeneous distribution of forces. Please remember that you have seen something similar in the bolted connections. Okay, do you remember it? Okay, if you don't remember, please study it because it's a very typical question for the exam. And one of the main assumptions in the bolted connections is that all the bolts are working homogeneously. Okay? So that's the end of the first part. We can have today we have 3 hours of lecture, right? Not 4. So we will end up with 2 hours. We can also not have all the 3 hours, but less than 3 hours. So let's have a 15 minutes of break. If people at home have any question.
Can you explain like the thing about the bolt connection? That's how it's similar to this.
Okay, sure. That refers to the first case when we are considering. This is very actually the traditional way where we can model how we can model a voltage connection. So basically, we have some force that is applied to the structure, and all the elements that oppose to that force have just the same stiffness. That means that this load is distributed homogeneously along all the elements. This is it. When we alter this hypothesis, it means that some element is working more than the others. Obviously, when we are dealing with torsion in a bolted connection, we have seen that we will have bolts that work more than others, but that's only because of the deformation of the blade, the deformation of the structure. When we see voltage connection with a shear force, obviously the shear force will be distributed along all the elements homogeneously. Okay, if we have no other question, we can have 15 minutes of break. Okay, guys, we can start the second part of the lecture of today. As I have anticipated in the outline of the lecture, this last part will be the introduction to the reinforced concrete material. Sorry, I completely forgot about it. Okay. So, this part of the lecture means to explain you. So, what is the reinforced concrete. Maybe some of you, any one of you already knows it. Maybe they have seen in some other course on technology of construction or something different.
More or less.
Okay, so someone already knows something. I don't know people from home, but so what is this peculiar material that is not a natural material, but it's handmade, human-made, handmade? Then a brief history of its development, of the development of this technology, which dates back in Europe, back to the ancient Rome, with some materials that were adopted that share a lot of similarities with concrete, and then the main mechanical properties of this material. And everything I will show you, everything I'm showing you for now will be only with slides and Blackboard. But at the end, if we have time, I would like to share a nice video with you, brief, because I am very sure that comprehension of things, when you see with your own eyes what is happening on a structure, is much more interesting than a lot of slides and theoretical words. But okay, let's start. I am recording, right? Yes. People at home can hear me?
Yes, yes.
Okay, thank you. So, as I said before, reinforced concrete is a material, but it is not a material. Actually, it is the combination of two different materials, basically the concrete and the steel reinforcement. Actually, also the concrete is not really a material. It's just a combination of different elements, different elements that, when they combine, they tend to create an artificial rock. Okay? And there are the steel reinforcement. Actually, when we look at any reinforced concrete element, we should never see the steel reinforcement, and I will explain it. I will explain why during this lecture, because it's a very important part of the structure and has to be protected. So the basic principle is that in any element, in any structural element made of reinforced concrete, steel reinforcement is meant to be placed where the structural element undergoes tensile stresses, okay, not compression ones. Why? Because the concrete, so the rock, let's say, the artificial rock, itself is not able to resist tensile stresses, and I will show that video that I was talking about also shows basically shows a compression test, a tensile stress, tensile test, and the bending test, in order to understand actually why the concrete behaves how it behaves and why the reinforcement is crucial. In fact, we know that concrete, as any other rock on the other side, is associated with a significant comprehensive strength, resistance, but a negligible tensile stress. In order to, so this works in principle, but what made possible the use of steel reinforcement in concrete structures is that two conditions are perfectly fulfilled, and these are two conditions on the materials. First of all, the adherence between the steel reinforcement and concrete. What is adherence? This is very important. The adherence means that in any point of the structure, we have, for example, typically, this is the schematic of, I don't know, a column, a beam, or whatever. Okay, this is very bad, but not meant to be. Nice. Okay, people at home maybe can see it because there is this. But if we cut the beam or a column or whatever, we can see that we have the cross-section of the head of a reinforcement bar, these cylinders in metal, okay? And these cylinders obviously runs into the beam at the same height, at the same depth. If we consider this cross-section, the deformation associated in this cross-section is the same if we consider the steel or the neighboring concrete. It means that both these elements, every part of the concrete right next to the bar undergoes the same displacement. Okay? So there is no sliding of the bars with respect to the concrete. This is something that can happen in the in the pre-stressed concrete, but it's a different behavior. In the classical traditional reinforced concrete, the metal bars have to be adherent with the concrete so that there is the same displacement in any section of the element. If there is the same displacement, there is also the same deformation. Obviously, we have seen that deformation is epsilon and stress is sigma. Same deformation does not mean same stress, and we will see it in a few slides. So adherence means same deformation between concrete and metallic bars in any section. Obviously, only when there is contact. We know that when there is bending of one element, we have we can have compression on top of the section and tension at the bottom. This means that the fibers on top of the section will not have the same deformation of the fibers at the bottom of the section, because here they will tend to have compression, here they will have they will be pulled apart, the two sides of the element. So we have elongation here. The adherence only refers to the close neighboring of the rebar. The second assumption that is fulfilled is that both the concrete and both the metallic reinforcement, so the steel, basically we're talking about steel, not iron, have the same thermal expansion coefficient. It means that we should know, I don't know if you know, but when we heat anything, like the cubic element of whatever material, when we heat this element, the volume will tend to increase. Okay? This is true because of the thermal expansion. Instead, when the temperature decreases, the material, any kind of material basically, tends to shrink. The problem is if we use some, I don't know, some plastic reinforcement, or some other kind of reinforcement, we have to be sure that the adherence is satisfied both in hot condition and both in icy condition when the temperature is very low, so that there is no sliding of the two elements. Okay? So it means that the two elements are expanding or shrinking similarly, basically in any climatic condition. So that's why we can use them, and we can combine them. Okay, now let's see how a reinforced concrete beam behaves under bending, because this is the important thing about the need to put a reinforcement in the structure. If we consider a homogeneous material beam, for example, some metallic, some iron beam, and we assume that the cross section is rectangular or square, whatever. We have this beam, it is supported at two ends, and we have a generic vertical load, transversal load, in this case vertical. The deformation of the element is obviously the bending deformation. So we have that the upper part is under compression and the bottom part is under tension. This can be seen also in the bottom part of the drawing. We have typically, when we have positive bending moment, tension at the bottom part of the element and compression at the top fibers. Obviously, if we are talking about stresses, if we integrate all the stresses in the tension area, or we just sum up, because integration is just a sum, and we integrate or we sum up all the stresses in the compression area, we will find that the resultant tension force is equal to resultant compression force. Okay. What happens when we are talking about reinforcement concrete? Well, in this case, in the reinforcement concrete, what we have seen so far is not actually true. Why? Because imagine that we have the same element, same section or whatever cross section, also a polygonal one, in reinforced concrete. We have said before that we want to put the reinforcement where we have tension. Actually, this is true in principle, but at the end of the day, for other reasons, we will put, for technological reasons, we will put also reinforcement when we have compression. But the main mechanical need to put reinforcement is only to absorb the tension. In fact, what we can see is that we have our cross-section. This cross-section is the one of a generic beam that is undergoing bending. Positive bending, what does it mean? We have tension at the bottom and we have compression at the top. What is this line? Here we have these two lines. The first one, the vertical one, is the line that represents this one. Okay, I should work on the slide, even if it's not so easy. The vertical line represents the underformed cross-section. The diagonal one means tends to represent the deformed cross-section. In fact, we have seen here that under bending we will have some deformation of the area, and we can imagine that of the cross-section, and we can imagine that the upper part tend to exert compression, and the bottom part is showing elongation. The main assumption we impose when we talk about bending in reinforced concrete elements is this one, the underlined one. The cross sections rotate remaining plane. Please remember this is crucial. What does it mean? That whatever the solicitation, in this case bending, the cross sections rotate, but they remain plane. They do not warp. They do not deform in their transversal cross section. So in this case, it is just rotating. And if we consider that previously there was the beam, imagine we are cutting it. We are cutting the beam here. Originally, here we have the beam. The new deformation will be the new side, the new face will be like this. So this part will be will exert some compression on the other part of the beam. This part will have an elongation, so will undergo some tension. The problem is, we have said so far that the concrete is capable to resist the compression, but does not resist to tension. So we have that the only element that can absorb the tension is the steel. We have seen before that if we integrate the tension stresses, we will have an equal level of the resultant in tension is equal to the resultant in compression for pure bending. In this case, if the concrete is not capable to resist to tension, it means that we will have no tension force, because there is no possibility to resist to tension, and so there will be no way to balance the compression, and so the element will fail. But we use this reinforcement here so that we know for the adherence assumption that these rebars, these metallic reinforcement bars or rebars, will undergo this stress, this strain, this deformation. And if we know the constitutive law of the steel, we can recover the level of stress knowing the strain. So we just integrate some stress that will be different, will be computed in a different way from what we do in the concrete, and we can find the tension force that is capable to counteract the compression force in the compressed part of the cross-section. It's important to notice that here we have an axis N, that is the neutral axis. This neutral axis marks the distinction between the compressed part and the tensile part. And the depth of the neutral axis is usually called 8x. Okay. Any question about this? Now, we can see what happens when we have a beam on more than one span that is undergoing a transversal load, distributed load. So first of all, as we have seen so many times, we should focus before on the deformed shape and then try to understand how this deformed shape translates into forces. So obviously, when we are in the span, in the first span and in the second span, we will imagine that there is a positive curvature, so a curvature with that tends to go upward, so here and here. Whereas in the internal, in correspondence of the internal supports, we expect a negative curvature. In fact, we can say that here the curvature is directed downwards. Curvature and bending moment, or better, are strictly related, or better, bending moment is our way to interpret the curvature in static terms. So when we have positive curvature, we have positive bending moment. When we have negative curvature, we have negative bending moment, with the maximum, obviously, in correspondence of the internal support. So what it means in terms of, okay, what do we do now with our beam of reinforced concrete? We're not talking about lines drawn on a blackboard. We're talking about possibly a beam. Here we cannot see any of them because it's not a reinforced concrete structure, but I told you before that we need to put the reinforcement where we have tensile stresses. So the bending moment is drawn like this, not just for fun, because we want some reference, and we say, okay, when it is positive, we draw it downward, and if it is negative, we draw it upwards. It's not just a meaningless reference, but it is a significant one, because we draw the, usually we draw the bending moment diagrams on the side where we have tensile stress. What it means that we know that if we have bending moment on this side, we will have to put some reinforcement at the bottom of the beam. Nevertheless, similarly, in correspondence of the internal support, we have a bending moment drawn upward. Okay, so we know that in correspondence of the internal support, we will have to put our reinforcement up in the top fibers of the element. So there is this strange path that should be done by the reinforcement. So at the bottom, in the spans, and at the top, in correspondence of the internal supports. What was usually done several years ago, nowadays, was that we could use, they used bent reinforcement bars. Now it is not that used because it is more expensive, but the idea is to use the same bars that walk along the path. I don't know, it's crazy, but this is the idea. So that's what we do. We put our reinforcement at the top where we have internal supports and at the bottom elsewhere. So if this beam undergoes that level of stress, the one that is associated to the transversal load, what happens is that the reinforcement concrete element cracks. Okay? we have cracks at the bottom fibers in the span, and at the top fibers in correspond where we have negative bending moment. Are we scared about cracks? Okay, they are not something good usually, but when we talk about reinforcement concrete simply does not undergo tensile stresses. So when there is a tensile stress, it cracks. That's how the material works. But the structure does not fail because there is also the reinforcement bars which works here and carries the tensile stresses. Okay, what I was showing you before here was a generic cross section with some part that is working under compression and some part that is not working under tension stresses, with only the rebars that provide some stress in the tensile side. But what does it mean? It means that we can consider all these parts completely cracked. Okay? So here we have some material that is resisting, here we don't have anything. So we may have some crack that reaches this level. Okay, before we go on, I wanted to see if I could share that video because I think that helps a lot also in understanding what happens. Okay, it's a very brief, I'm not going to lose too much time about it. It's on YouTube. Is it working? No. Okay, basically this is the video of a guy that casts its own elements of reinforced concrete. And here it performs a compression test. Okay, it was quite fast. But that's the point. When we have a generic element in concrete, here we're talking only about concrete, there is no reinforcement bars. This generic element was capable to undergo a compression level of 450 kilograms. This is how the failure appears. And that was a compression test. So just a vertical load that tends to compress the sample. Now, this guy does the same stuff on a tensile stress. So rather than shrinking the element, it tends to pull apart one side with respect to the other. So hanging a weight at the base of the element. So it increases progressively the load, and the sample fails. Here there is not any drawing, but at a level of weight of 33 kilos. Before it was 450. So that's why we were saying before that concrete behaves very well in compression, but performs very poorly in tensile conditions. now let's switch to the behavior in bending. So there is the casting of this concrete beam, and again it is just a concrete. How we can perform a bending test? This is a typical bending test. We have 4 points where the load is applied. The 2 ones are basically the rollers, okay? Because here the element can rotate and can undergo any kind of displacement, but not a vertical one. And we have a vertical transversal load applied on 2 elements. Here, in this part, we will have, we can imagine that this load is 1/2 applied here and 1/2 applied here. So it is as if we have an horizontal beam with roller, 1/2 of the load applied here, 1/2 of the load applied here. And we know, if we compute the diagram of the internal forces, we know that in the middle there is a constant bending moment. So, what happens to the beam? The beam progressively bends. These lines tend to magnify the behavior of the bending, and here we can see that this part is shrinking and the other part is undergoing an elongation. So this is what bending is. Even if we have no horizontal force applied, and this force, this compression force, is exactly equal to this one. Problem is that at the bottom we have tensile stress, and we know, we have said, and now we are seeing that concrete has no tensile strength. So when does it fail? It fails at the bottom. Okay? So a crack starts at the bottom and develops upward. Because I showed you that when a crack occurs, the element survives until there is the possibility to counteract compression with tension. But the compression side is progressively reducing because there is no element that is capable to resist, to survive to tensile stress. Okay, blah, blah, blah. Okay, this is what happens when this guy puts some metallic bars at the bottom of a beam element that is cast exactly the same as before. He performs the same test. This time he needs to apply a higher load. But what's most important is that we can see we have already some cracks. Okay? So the fact that a reinforced concrete element is cracked does not mean that it is failing. And we can see cracks basically in almost every reinforced concrete structure. And that's the perfect representation of, of what I showed you before. Here we can imagine in the upper part of the cross-section, for example, here, the neutral axis that reaches this point, for example, or maybe this point. I cannot see if this is a crack, but we can think about this. The neutral axis so far is at this depth from the top of the bar, from the top of the cross-section. From this part to the bottom, there is a crack, so basically there is no exchange of stress between this part of the structure and this part of the structure. So the concrete is ineffective here, but there is the metallic rebar that we can see here and that we can imagine here. this rebar is providing the same strength, the same stress, tensile stress that is provided by the compression in this part. As the load increases, the bending moment increases, and the cracks propagate. The load is okay until the failure. And this is the most important thing that we are interested in when we talk about reinforced concrete. The difference between reinforced concrete and simple concrete is that in this case, in the first case, we have a brittle behavior, fragile. Okay, it means that fragile does not mean that it breaks immediately, but it means that the failure is associated with a very small deflection of the element. So we cannot see if one element is going to fail or not. The opposite behavior is the ductile behavior, duttile in Italian. That means that the structure, before failing, undergoes greater and greater displacement. And that's important because it allows us to understand that something is going wrong and that we can just walk outside the building before the failure. It's not related to the level of stress and the level of load that can be faced. It is applied, it is associated to the level of deformation. And you can see these are metallic rebars. We can see that these are not cylinders. Okay, there are these strange parts. What do you think these elements need for? Are meant to be? Do you think that they have a purpose or not? Yeah. Yeah, to increase the adherence. Because otherwise it can slip over. So let's go back to the slides. Now, I think that that video helps a little bit in just understanding what these elements, what these drawings means, even these, and to understand why reinforcement bars are very important in reinforced concrete. Okay, now a very brief background history of the concrete. I don't want to spend too much time because you have the slides and you can see it. But now we're talking about concrete, not reinforced concrete. Everything starts with the opus cementitium in the architecture of Vitruvio that allowed in ancient Rome even to build the Pantheon. That is a great cupola with a great dome with a very great diameter, and it was feasible. It was made feasible by the use of this material. Basically, the logic is to use a lime mortar, in Italian it's a calce, in order to increase the adherence, not the adherence, but in order to mix better the aggregates of so the small rocks, the broken rocks, that compose this material and to make actually an artificial rock. So no news came apart until the 19th century with Hayat, which started studying not only theoretical but also experimentally reinforced concrete structures. Let's think about the fact that the high-rise buildings before the 20th century were mainly not residential. For example, the Eiffel Tower was in steel, and it was clearly not a residential building. Whereas the first skyscraper in the world in reinforced concrete and also in other materials were like 10 floors, 10 stories, or 12 stories. So it's only with the use of modern materials that we can reach higher heights. But let's stick to the reinforced concrete. We're talking about Hayat. And here we can see the drawings of its patent. And here we can see the path of the reinforcement that have to be put into concrete elements. Obviously, when we have the internal support, we have already seen that we need to put the reinforcement not at the bottom of the structure, not only at least, but mainly at the bottom, at the top. Then we, in the 1892, the patent of Hennebiek, which studied similar behavior, similar structure. This patent is about the beam with steel reinforcement that were cylindrical bars. At the time, the bars were really cylindrical because still they had not the importance, they didn't really know the importance of adherence and how to increase technologically the adherence between steel and concrete. And he also added the use of stirrups, in Italian staffe, in the transversal direction. We have seen so far the longitudinal rebars. Here, these longitudinal rebars are usually meant to absorb tension that can be provided by bending or by tensile condition on their own. We are not talking about transversal elements. Transversal reinforcement. The transversal reinforcement is meant to provide some reinforcement to the reinforced concrete with respect to the shear force. The behavior of shear of concrete under shear force is not so simple. It's not that tough actually, but will be the last topic that we will see. I don't know if next week or in January. But to absorb shear force, we do not need longitudinal rebars, but transversal rebars. And usually, I don't know if there is a drawing. No, there is no drawing. These transversal rebars not only need to something like these, mainly, are just something that confines the section, and they are placed at specific distance, so that we can see something like that. The importance of stirrups is not only to absorb shear forces, but also to provide confinement in the reinforced concrete elements. Now, starting from the end of the 19th century, a lot of bridges were designed and realized using reinforced concrete elements, and in this case, we can see the bridge in France, another bridge in Rome, this one spanning 100 meters, so very long, and even bridges in with higher freccia in Italiano, with higher heights. It is very interesting to look at bridges because when we look at the bridge, we only see structure. We do not see anything else that can prevent us to understand the structural behavior. In this case, for example, we have the arch, and obviously the arch works in compression. Then we have these other elements, these columns, let's say, which transfer the load from the deck of the bridge to the arch. Then going along, we have other examples of low-rise bridges with arches spanning more than 70 meters and even 180 meters here in France again. And they're all by Ennebic and Fressinet, basically. In recent years, also Maillard, we have here the possibility to design and realize bridges also in locations that are not very comfortable to bridge a structure in. But okay, I will not lose so much time about it. And now we can see the mechanical properties of the reinforcement concrete material. This last part of the lecture will meant to provide you some useful information about the mechanical behavior of the reinforced concrete, and then we will use what we are seeing now to understand how reinforcement concrete elements perform in pure compression, pure bending, and combined compression and bending behavior, but next week. It makes no sense to put a lot of information in your head or in the morning. So here we have this drawing. Okay, it is in Italian, I apologize. This is the stress-strain plot, or that describes the rheological behavior of the reinforcement concrete. Here it is Calcestruzzo. Actually, it should be. Oh no, this is only concrete. I guess only concrete, not reinforced concrete. On this side, where there is the main part of the drawing, there is compression, and on the other side there is tensile stress. Basically, what does it mean? I mean, I have shown this plot to several students before you, and I always have the feeling that it is very simple to understand it, but actually not really. So, in order to understand how this behaves, or better, what is the meaning of this drawing, it is better to explain where it comes from. So this is basically what is it? This is a curve that correlates the stresses to the deformations, to the strains. What can you understand from this plot? First of all, that we start from 0, 0, okay? When the element is not undergoing any load. Assume that we are working in compression. So, for example, we have here, I don't know, people at home can see it. Maybe I should stop. You should be able to see it. Here we have our sample of concrete, and we apply compression force. Similarly to what did the guy in the video I showed you. Basically what happens, increasing this force, there is also an increase of stress. And similarly here, for equilibrium. So we know that the stress is simply the ratio between the force applied and the area over which it is applied. This is the geometric, the projection of this sample. So this has a generic area of A. So we start from the unloaded element. We apply progressively increasing load, external load, and this sample tends to shrink, obviously, okay? So we start with original H, capital H, and then we end up with, I don't know, H1, this is H0. Basically, we can say that the ratio between the new H, the new height, and the original one is the strain. So we just compute this level of strain associated to that level of stress. Sigma epsilon. We apply a load sigma 1 and we find epsilon 1. Then we increase the load. What happens is that the sample shrinks more. Okay? And for example, if we double the load, we will have sigma 2. And at the very beginning, we meet epsilon 2. We see that the the epsilon is the deformation, so the difference of height over the original one. Apologies. So we double the load and we find basically the double of the strain. If we increase so far, progressively increasing the load, we see that we are moving along a linear path. Okay? Actually, for the concrete, if we increase linearly the sigma, the stress, or the load, the epsilon, the stress, will not increase perfectly linear, but will tend to be always a little bit less than what they should be in the linear case. So this linear assumption holds only for low levels of stress. the real behavior of the part. So actually, it is as if it is decrease deforming more than what it should. So if we say sigma 5, so 5 times the original one, we do not meet 5 times the epsilon, but we will see more than it. Okay, this is the assumed one. In the linear case, this is the real one. So the concrete is not perfectly linear. It is roughly linear for low levels of stress. As we increase the load, we reach the maximum level of stress. Then, obviously, what happens is that if we increase again the load, it will fail, because it is not capable to undergo higher levels of stress. But if we are capable not to control the increase of load, but the increase of the formation, we are capable to follow the path of this sample until this point. So we can see that the true behavior of stress strain is like this. This will come into help when we will need to compute the bending behavior, the behavior of in bending condition. Okay, and we will need to know how to move from stress to stress strain to stress, because this is what happens for the concrete, but the steel will behave differently. And we have said before that concrete and steel, when the perfect adherence holds, will have the same level of strain, but obviously not the same level of stress. Okay? Instead, if we look at what happens in the other side, so we're not applying the compression force, but the tension force. So we're trying to pull apart this part from the other one. Maybe we can hang it to a rope, hang it to the ceiling, and then hang the load on this sample, increasing the load. Again, initially we are linear, but then we immediately reach the failure, because it is not capable to absorb high levels of stress in tension. So I hope that this is clear. This is that plot, okay? And this is epsilon 0 associated to the maximum level of stress, but the ultimate compression strain for concrete is higher than this one, and this can be seen as a sort of little ductility behavior of the material, but it is very small. So, in fact, the concrete is a brittle material, not a ductile. If this sector would have been higher, we would talk about a brittle material, a ductile material. And then this is what happens in fraction. This is the initial, yes, correct. This, the inclination of the slope of this curve is the Young's modulus. In fact, we remember, I hope, that in the elastic case that holds also for steel, but it holds for generic behavior, the correlation between stress and strain is linear and is ruled by the value of the Young's modulus. Okay? And in this case, we can assume that also concrete has a Young's modulus ET that allows us to translate strains into stresses. And this is obviously not. You will see it in a while. So we can go on. This is something very important. The first plot is quite important and tell us what happens when we do not run the load test until the failure, but we do something smarter. We come back here. You don't need to draw it because it is just to fix the idea. Imagine we start with a virgin sample, so unloaded. We perform an initial loading path, so you impose initially some compression. What we see is that we run along that path that starts linear and then starts to be nonlinear. And so starts to accumulate non-linear deformations. When we stop, if we stop at a certain level and we unload the material, what happens? We will not walk through the original path backwards until the original level O. But when we remove completely the load that we had applied on the structure, we will walk along a perfectly linear slope that ends up here, O first. Okay? This, the slope of the unloading path is the same of is characterized by EC, so the Young's modulus of concrete. What does it mean? That we have accumulated some non-elastic, so let's say non-elastic, it could be seen as a plastic deformation because it is some deformation that is applied on the structure and now is unremovable, so it's permanent. And when we will reload again, we will move along this line. So we have pre-loaded the sample, the material, and now we are in a perfectly elastic linear case. So when we will load again, we will move along this path, perfectly linear, and then when we remove it, we will return to the original path. And from this point on, obviously, the nonlinear behavior is the same of the unloaded sample. The problem is that the Young's modulus is not a fixed number because it depends on several properties of the material. We have said that the concrete is made of cement, of lime, and of rocks and other elements. So, depending on the properties of the aggregates and of the additives, we have the possibility of that the values of Young's modulus are quite spread, not so much, but they show some dispersion. Okay, they are quite scattered. This is associated with the impossibility to have a perfect characterization of the material. And so, different codes provide some formulas in order to estimate the levels of the Young modulus depending on the failure stress, the characteristic compression stress of the material. So we just have different samples of the same material. We perform some compression tests on them. We know at what level most of them will fail, and then knowing that level, that is FCK, but I will explain it in a couple of slides, we can understand, we can estimate the Young's modulus. And here we go. The deformability. How to infer the Young's modulus. I showed you in the previous slides, one of the first one actually, okay, here, that the materials in reinforced concrete are usually, carry usually this denomination, C2530, or something different, but it is a C followed by two numbers. In this case, it can be C2025, C3037, and so on. These two numbers refer to the characteristic compression stress of a cylindric sample or of the cubic sample, because compression tests can be performed or on cylindric cubic samples or on cylindric ones. Okay. Due to the geometry of these elements, cylindric elements are most landed, and so they will fail with lower levels of stress. It does not mean that they are weaker. It is just an effect induced by the geometry. So, the compression tests are very standardized. When we perform a test, a compression test on a sample, the dimensions have to be fixed. All the ratios between the height and the diameter of the cylindric have to be fixed, or on the dimension of the square, so that we can know what is the level of stress associated to the failure for compression, and then estimate the Young's modulus. And here we have, in the Italian codes, in European code 2, and so on, in other codes, the values of Young's modulus, so the initial one or the second one. So, we said that initially we go along a path, a slope, and then we follow a different one. So there is the initial one and the second one. Okay, something strange about about the concrete that I have not yet mentioned is that the compression, the mechanical properties actually vary along with time. So what does it mean? If I cast some beams today, obviously, how is it cast? We have you have seen it in the video that I have shown you before. We have some structure that that we have to use, for example, in wood or some other material. We put inside rocks or little pieces of rocks, then some powder, that is the cement, and then water. We just use these three elements. we let the cement actually put everything together and react with the water in order to create something stiff. And then all the structure that we have created with the wood, we can remove it and throw it away. Obviously, this process of maturation of the concrete takes time, because initially it is fluid, then it solidificates, and then it becomes stiffer and stiffer. So if we wait, the more we wait before putting the load on the structure, the stiffer the structure will become in the future. Basically, independently from how we load the structure, the Young's modulus will increase in the future. Initially, it is an exponential increase. It reaches its a standard level of resistance after 28 days, so from 0. And then the gain we have in resistance is less and less. So this is what happens. And please notice that this is not a linear diagram, so it is 0 days, 28 days, and then it becomes months and years. So it means that going along with years, we gain some more compressive strength, but not that much. Okay, here it is the diagram I was talking about. We have increased on the Young's modulus in this case, after 7 days, 28 days, 45, 90, 180, and you can see that this path is increasing slower and slower. Okay, now just a few words about this, because it is quite important before we see it next week. I have talked about before the characteristic compression stress. Does anybody of you know what characteristic means? Is it just some random word I have used, or it has a meaning? You have not seen it in different courses, right? Not because it is related to statistics. Basically, when we have, I said before that every sample of concrete depends on the aggregates I put into, on the quality of the cement, on the quality of the aggregates, of the rocks, and on the ratio between the cement and water. So, theoretically, every sample is quite different from the other. of Lübeck. Maybe there will be some weak pieces of rocks here, and so I will have some weak surface that can induce some failure of the material before the time when we perform some tests. So, if we perform the test, some compression test on 100 elements, on 100 samples, we will find that, here we can say number, we can plot the compression stress that is associated to the failure of all the 100 samples. And maybe it is something like that. Okay? Most of them will fail, I don't know, 25 megapascal. Some of them are more resistant and will reach 28. Only few of them will resist more than 22. Similarly, almost all of them will resist more than 20 megapascal. I think you have already seen this kind of diagram with Professor Gentile when it was talking about the steel, because I think that you should have seen similar stuff. But the idea is that this is the mean value of the compression level that is associated to my population of samples. Okay? But when I do my computation, am I really sure that I want to use as the value that I use for design that mean 1, even if it is associated to the most part of the samples? I mean, I know that if I consider from all my samples, and so the samples are extracted from the concrete that I'm going to use for a building. If I have to do my computation for that building, my safety computation for that building, maybe I don't want to use the level of characteristic of mean average compression stress that is associated with the samples that I have used. Because I know that 1/2 of the samples, roughly, will be able to carry on, to carry this level of stress, but 1/2 will not. Okay, so that's not a very smart thing to do. So that is the mean cylindric compressive strength. Then there is the characteristic cylindric compressive stress. That is the one associated with this area. And this area is not the... Okay, let's start from this in order to make it clear. The mean one is basically, roughly, associated to the 50% of the samples. Okay? But if we focus about the 5%, so not all of 1/2 of this curve, but only the 5%, we are talking about the characteristic value. Okay, you can say, how can I understand the 10%? We will not use this curve that is simple to understand, simple to interpret, but we use a different curve where we accumulate these numbers. So it will be every time I see a new failure, I just add it in the ordinates. So I will reach the maximum, that is the total number of elements. So when I know this is the 5% of that number, I will find the ordinates this is the total, this is 5%. And it is the characteristic value. Okay. This is something that is usually adopted, but for our purposes, when we perform the computation, the design, we do not use the 5%, but the 0.5%, or 5 per thousand. Okay, this is the design value. FCG. Compression, C stands for compression, D stands for design, F means that we are referring to the compression value of cylinders. The capital R stands for cubic samples, not cylindric ones. Whereas SCT, SCT cap, K, SCTD, when we have the T, stands for tensile. Right? So, we always focus on design cylindric compressive strength. Now, these are just some images of how tests are performed, but we have already seen the video. So if you want to know something more, you can look for other videos online. Basically, we cast several elements and we perform a compression test on each of them so that we can run some statistics. We try to understand both the level of stress that is associated to the failure and on the typology of failure. If it is a regular one, so basically symmetric and pyramidal, or an irregular one. Okay, and this is just to stress out that depending on the geometry of the samples, also the level of stress will vary. But it does not mean that the material is less or more stiff, it just means that geometry has a role. But it's not very important. Just end up with, we will see every time that a concrete is characterized by this sigma, that is a capital C, stands for concrete, and two numbers. The first one is the characteristic compression stress associated to cylinders, and the second one is the characteristic failure, the compression stress associated to cubic cylinders. And obviously, the second one is always some percent more than the first one. Okay. Is there any doubt? No? People from home? Okay, so we can see next week. And we can see the behavior of concrete, reinforced concrete, under compression, bending, and combined compression and bending. See you guys. Have a nice weekend.